Good. All right. So Maxwell's equation before Maxwell, it's not like they didn't exist. We've seen a bunch of them, right? And they're named after other people. And they didn't really exist in this form. The form I'm going to show you to remind you of are all the ones we've seen, and they're all in differential form. They really existed in integral form or other forms. So, but let's write them down. So first we saw Gauss's law, right? Where that's the charge density. The rho is the charge density. This is Gauss's law. And then we saw this equation. It doesn't really have a name, but I would call it no monopoles, no magnetic monopoles. That's what I call it. And then we saw this one where if you have a changing magnetic field, you get you generate, well, you have a curl to E. And this is called Faraday's law, which is the one we just saw. And then we saw a while back in magnetostatics Ampere's law. And this J is the current density. Okay, they were all known, but there's kind of there's a fatal flaw in these equations. And Maxwell is the first to realize there was a fatal flaw and fix it and kind of cohesively put them all together. Okay, they were kind of scattered about. Okay, I'm not sure anyone even wrote this down in this way, like, certainly not in differential form, but not really all in one thing, right? He really did a lot of work and that's why they're called Maxwell's equations, because he did a lot of work, not just fixing the flaw, but showing that these equations give you the wave equation for light, etc. Okay, so let's look at what the fatal flaw is. So we're going to look at this equation. Oops, my bad. Let's go down. Okay, so we're going to take the divergence of both sides. And that's going to give me the divergence of I'll put a negative sign out, of partial B, partial T. Notice that this thing here, this is the operator div curl, which is always 0, right? When div curl acts on something, it's always 0. So this is 0 on this side. And then over here, I'm going to keep going. I can write this as negative ddt of del dot B, right? A del dot B, we know, is 0. So we are good, right? There's nothing weird about this. We have 0 on both sides. Okay, that's great. Let's do that for the other curl equation, right? Ampere's law. Let's go to the next. Let me just copy this there. Okay, so I'm going to erase this now, and we're going to do it for the next equation. Oops, my bad. Okay, so we'll do that in yellow here. All right, so let's do it. We're going to take the divergence of both sides. And we have mu 0 del dot J. Okay. Again, on this side, we have div curl, and that's going to give us 0. But over here, we have a little problem. Now, it is true, we've said it before, that del dot J is 0 for steady currents. Yeah, but it's not in general true. If you have a current that's not steady, and there's lots of situations in which a current isn't steady, right? When you're ramping up a current in the circuit, right? It's not steady. So in general, remember that this guy here in general, del dot J is, oh, I forget the, is this their sign? Yeah, minus partial rho partial T, where that's the charge density, right? Because if the change is kind of the change in the current is proportional to how the charge density is changing with time, right? Because you're moving along some volume charge or something. Yeah. So it's not zero. So this is, we got a problem here. Not equal zero. Right? We got a problem. This is an issue. Okay, let's look at it a different way. And I'm gonna go and just get a new layer for this. So let's just look at a circuit. Got a battery. And we've got a capacitor. Okay. And there's our battery, and we have an some current flowing through the circuit. Okay, simple idea. Let's put an Amperian loop down because we're dealing with Ampere's law, right? Okay, so let's put an Amperian loop down. I'm going to put this loop and I'm going to put it here. And it's enclosing the wire. It doesn't look like it, but yes. Yeah, it's enclosing the wire. Fine. It's Ampere's law in integral form says that the integral of B dot dl around that loop, right? Remember the dl is around the loop here. dl is going to be mu 0 I enclosed, which is just mu 0 I because I is flowing around that circuit. Yeah. Okay. And we can just assume here that the capacitor is in its charging mode, so it's taking its time to charge up. You know that once it's fully charged, the current doesn't flow anymore, but we're in the region in which it's still charging. Okay, it's got to work for everything. All right. Okay, so that's fine. So as we know, right, the I enclosed is the current passing through the surface that's bounded by that loop, right? Isn't it? So if we were going to draw that surface, let's see. I need a good contrast. Let's see. Right, it's a surface bounded by the loop. Yeah, that's the I enclosed. Okay, so I that pierces that surface. Okay, but we are free to take a whole nother surface if we want to, right? As long as so in other words, this part here, and I should put a little P around there. This should be a loop P. Okay, that will be the same. If P is the same, that part will be the same, won't it? Okay, so I'm going to take another surface that's also bounded by P. Okay. So I'll draw the circuit again. Draw the circuit again. We still have our I. Okay, let's draw P again. So P, there's P, right? But my surface is going to be different. It's going to be a little bit like a sock. Okay, and that sock's going to come over here like this. Okay, and now that surface is like you just put a sock on, right? And the sock, the foot of the sock is over there at that edge. And the opening where you put your foot through is P. You agree that that surface is bound by P, yes? Just like the topology of your sock that you have on your foot, unless you have holes in it somewhere besides where you put your foot in, the rim of your sock where you put your foot in is the boundary of your sock. It's not the shape of the sock or anything. It's that hole, the rim, right? Okay, So this is bounded, this surface here bounds P, but P didn't change. Therefore, this guy here is the same. Because P is the same, right? However, what is the current that pierces that surface? So just to help your thinking, imagine this circuit is in a vacuum. And we pulled a sock over one side of the capacitor. Not touching the capacitor, but we have a sock, right? So what current flows through the surface now? Huh? Well, I mean, it's not a real sock. I'm sure a real sock would do something. But, right? But that's the topology of what we're doing. Pulled a sock on it, not touching anything. And we want to know what current is actually piercing through that surface the way this current pierces through here. Does current flow between capacitors? Two plates of a capacitor?
No.
No.
So it's zero.
Zero, right? Because the way the capacitor works is charge builds up on this plate, which induces charge on this plate, which pushes the current around until it's fully charged and then it stops. Right? Because it only has in the capacitance to hold a certain amount of charge, right? Yeah. Given by its capacitance, obviously. All right. So it's zero. It's zero over here. So, right? We now have the exact same integral here because P didn't change. But because we chose a different surface, we get different answers, which is not good because if this is 2, this will be 2, and this is whatever this is, and this is 0. So now you've got a problem, right? And Maxwell was the first to look at that and be like, this isn't right. Okay, so here's how he fixed it. All right, so let's recall again that we have del dot J is minus the change in the charge density with time, yeah? And remember that this guy, partial rho, partial t, is partial t of epsilon naught del dot E from the Gauss's law. Yeah, I just solve for rho. Good with that. And then I can switch everything around and I can say, okay, this is epsilon naught del dot, oh, maybe I'll keep the epsilon naught in there. Epsilon naught partial E partial T. So I just switch the order of derivatives, which I'm always free to do. Okay. Okay. So the correction is, right? Because remember, let's go back to where our problem was. Well, hold on. No. Wait, what did I do wrong? There, okay. Where our problem was here, right? When we take the divergence. Okay. So what we can do is replace the divergence of J with that d rho dt, but written in terms of E. Okay, so let's go back. So what he did was like, let's just correct this equation. So the equation becomes del cross B is equal to mu 0 J, which is what we had before from Ampere's law, but plus mu 0 epsilon partial E partial T. Yeah. Now, this is a lot more symmetric, okay? So if we go back to the beginning of Maxwell's equations, right? We call this guy del cross E is equal to minus partial B partial T. This we said was changing magnetic fields induce electric fields. Right? But now you can see up here, changing electric fields induce magnetic fields as well. So that was also the issue too, is that, there was some weird asymmetry there that was confusing because Maxwell knew that if you didn't have this property that changing electric fields cause magnetic fields and changing magnetic fields cause electric fields, you really couldn't have light. Okay. So that's the change that he made here. So Ampere's law is, the true Ampere's law is here. Okay. All right. So let's just go back and just show how, I mean, I think we have an idea how it fixes everything, but let's go back and look. Okay. My computer's doing its thing again now. But we're at 81%, we'll be all right. Okay. Okay, so let's just look at our capacitor example, right? So let's let our capacitor be, close together. So a little parallel plate, but really close. You don't have to do this, but it's the easiest way to show, okay, just for ease. Then I know what the electric field is. If I'm really close, it's just 1 over epsilon naught sigma, the charge density, right? We've seen this before, okay? N hat, okay? And then I can write, okay, well, that's just 1 over epsilon naught, the charge over the area, right? That's what sigma is. And I'm gonna now, sorry. I'm gonna just write the magnitude of E. There we go. Okay. All right. So then dE dt is going to be 1 over epsilon naught A dQ dt. Okay, we don't expect Q to depend on anything but time. And then 1 over epsilon naught A, and that's just I dQ dt, right? Okay. So when we do our Ampere's law business, where we take our integral over our B dot dl, that's going to be mu 0 I enclosed, but then plus mu 0 epsilon naught, the integral of partial E partial T dot dA, right? I'm just moving from the differential form to the integral form, right? That's all I did. You agree with this? Okay. Okay, so now for our first surface, right? The flat surface. Okay, we know that this is P, so I'll put P here. Okay, oh, it should have been orange, but whatever. You get it? Okay. We know this thing is whatever it is, like 2. Okay, so that's fixed. And we know that we're going to get mu 0 I in our circuit over here. Okay, but here E is 0, right? There's no electric field over on the, wire, basically, right? We're not going to let, there's no there's no buildup of charge. It's just current, right? Okay, so this part is 0. But then when we have P and it's a sock, right? We have the integral P B dot DL, which is the same exact as you get up here, right? But on this side, there's no I enclosed, so this term is 0 plus mu 0 epsilon naught, right? But dE dt is 1 over epsilon naught A, and then we have the integral of I over A dA. Oh, wait, my bad. I already put the A in there. dA, right? And then this thing here just becomes the I comes out. Again, this is just an example, right? It's not the most general case. And then the integral dA becomes just A. And you get up here, the EDT, 1 over epsilon naught A. I just left my mu naught out. Yeah. So mu naught, right? Sorry, I'm losing track of all my terms, my pieces of epsilon, of mu naught. Okay, so we started off with mu naught epsilon, and then we have another epsilon. You're right, the epsilons will cancel. I left out an epsilon here, so that should cancel, right? And then we just get mu naught I over A times A. In other words, mu naught I. Same answer, right? Same exact answer. Okay, so that's kind of how the fix works. Yeah. And that's all I got. Okay.
What time does the final open school?
It opens tonight at 8. Yeah, I changed it.